This video is going to show you how you can use the I2C protocol to output from your Android Things application. We'll discuss the Raspberry Pi Rainbow Hat and its actuators, in this case the 4-digit alphanumeric character display, which we'll use to count down from 1000. Let's get started. I2C, or I²C, stands for Inter-Integrated Circuit. I2C works with multiple pins on your board, but only uses one pin to transfer data. This is known as a serial interface. There are 3 pins involved: a clock pin, the data pin, and a ground pin. I2C has a master device that controls communication initialization and multiple slaves, each individually addressable. But don't worry, Android Things abstracts most of this detail away for you. Our Raspberry Pi is now plugged in and connected via ADB, ready for development. We have the Rainbow Hat connected to the top of our Raspberry Pi. This hat has a lot of peripherals, and amongst them the HT16K33 4-digit segment display. We are going to code our app so that it will count down from 1000 at 0.1 second intervals, showing this count on the Rainbow Hat segment display. The segment display can't be missed, it's raised up in the middle of the Rainbow Hat board. To understand how a peripheral works and determine the protocol needed to talk to it, we should consult the Rainbow Hat documentation and, if needed, the specific peripherals datasheet. In the documentation shown here, we can see the 4-digit segment display described as 4-digit alphanumeric character display, and it says it is via HT16K33 I2C 0x70. This is the hint we need to tell us to use the I2C protocol for our communication with the sensor. The 0x70 is the individual I2C address of the sensor, and HT16K33 is the name of the chip that will drive the segment display. As it suggests, we should read the datasheet if we want to know more details. I2C is the communication protocol for sending packets of bytes. However, what is contained in those bytes is proprietary to the actuator. For example, this 4-digit display shows characters, but how do we know what form in binary the characters take? And how do we know what to send when, or if we should send requests for brightness, or if there is a need to turn the display on or off? For this information, we have to check the datasheet. Let's do that. A quick Google gives us an Adafruit datasheet for our actuator. Let's keep this tab open for later reference. Okay, let's program the temperature sensor. Here I have an Android Things project already set up in Android Studio. If you aren't sure how to get your project to this point, you can revisit the previous first app lesson for instructions. First, we create an instance of Peripheral Manager Service using this code. This is the Android Things SDK class that allows us to open connections to different board pins using the different available protocols. Using this instance, we want to open an I2C connection. The open method takes 2 parameters. First is the pin address we saw earlier on the pinout diagram, and the second, the individual I2C peripheral address we read in the technical documentation. When we open this connection, we are given back an I2C bus variable that will now allow us to communicate using the Android Things SDK I2C class. We'll use this variable in multiple Android activity lifecycle methods, that's why we make it a field. Notice that we have to wrap the open I2C device call in a try-catch block. This is because the method, and most of the methods we will use in the future, all throw a potential I/O exception. This is due to the fact that we are dealing with hardware, and at any moment the pin or the peripheral could become unavailable, for instance because of a loose wire. At that point, calling the method would throw this exception. We are assuming that all our wires are nicely connected, and if we do get one of these I/O exceptions, it should be really bad for our app, and actually we want to crash straight away, so we can diagnose the problem as soon as it happens. That's why in the catch block we throw an illegal state exception, as we are not expecting nor wanting this to happen. This is known as failing fast and is a clean code best practice. The benefit of this is our bus variable is either a fully instantiated field at this point, or our app has crashed. Therefore, from this point on, there is no need to check if our bus field is null, it never is. Opening a connection to a pin is capturing this pin as your resource, and like with all resource management, it is good practice to release resources once you have finished with them. Also, if we have an open connection to a pin, no other code can open a connection to the same pin until we close our connection. Since we open the connection to our pin in the onCreate method, we should use the symmetrically matching pair from the Android lifecycle to close the connection. Therefore, we close the I2C bus connection in onDestroy using this code. Again, close can throw an I/O exception. We can't do anything about this if we get an exception, but we can log it out so that we know next time our app starts if something unexpected had happened in the past. Let's create a handler that we can post runnables to. These runnables will count down from a set number at a fixed rate. We create the handler using our own handler thread looper, meaning we post messages on our own non-UI thread. We are counting down from 1000 and it could take some time, so we don't want to do this on the main thread. We have a field to declare the number we are counting down from, in this case 1000, and we have a variable which will start at this number but be mutable so that we can decrement it every time we post a new runnable to our handler. These look like this. Now let's create a runnable to post to the handler with this code. This runnable will decrement the counter, and for now, we will print the number to logcat to ensure our looping is correct. After logging out the number, we post this same runnable again with a delay of 100 milliseconds to create a loop. This means we will decrement our number 10 times a second, so it should be quite fast counting down. When we reach 0, we want to stop posting more messages and return early. From reading the datasheet on page 8, it explains, when the system is first turned on, it is in a standby state, with the system being off and display being off. Moving to page 10, the datasheet explains how to exit standby mode. This will turn on the system. Looking at the table here, it shows that turning the 8th bit to a 1 will turn on the system, and that this system set byte has a hex definition of 20. This means we can turn the system on using OR bit manipulation in Java. Let's do that now in the onStart method. To write a single byte with I2C, you could use the write_reg byte method. However, write_reg byte requires a register address, and as we saw from the datasheet with this peripheral, the register address is combined into a single byte. Therefore, we use the more raw form method, write. Write allows you to send as many bytes as you want without a leading register. In our case, we are just sending this one byte. We throw an exception if we can't get the app out of standby. Now the system is out of standby, we also need to turn the LED display on. Reading page 11 of the datasheet, it explains the display setup register, showing how to enable and disable the display as well as other settings such as blinking. Looking at the table, here it shows that turning the 8th bit to a 1 will turn on the LED display, and that this display set byte has a hex definition of 80. This means we can turn the system on using OR bit manipulation in Java. Let's do that now in the onStart method. Again, we use the more raw form write method as explained earlier. This allows you to send as many bytes as you want. In our case, we are just sending this one byte. We throw an exception if we can't get the display to turn on. We've been reading the datasheet for the LED driver. The LED segments themselves have their own data format for encoding characters. This can be looked up online. For simplicity, I've recreated just the 0 to 9 byte formats here, as this is all we will need. To look up our count digit in the map, we need to convert it to chars. We do this with this code. Notice we are padding out the characters with leading zeros. This gives us a nice left to right formatting and stops ghost digits, for example, a 1 being left written in the first segment when we move to 999. Now that we have our number we are counting down from as an array of characters called digits, and we have the map to look up the byte value for these digits, we need to know where to write the byte encoded digits to. Page 13 in the LED driver datasheet explains about the display memory. Each row output corresponds to one of our segments in our 4-segment display. Therefore, we can use the hex values 0, 2, 4, and 6 to address our segments left to right. It also gives us a table showing the data format for the encoding digits. Because we know our encoded digits are 2 bytes long, we can use the I2C method write_reg_word, giving it the register addresses from the datasheet and our encoded digits that correspond to the number we are counting down from in this loop of our runnable. That's done with this code. Hook up the runnable to run when the app starts, adding this code to the onStart method. Remember, the runnable repeats itself by posting again every time it gets to the end, and for best practice, always remember to remove callbacks using the Android lifecycle symmetrically matching method, which in this case is onStop like this. Let's run our app and watch the I2C protocol working as we count down from 1000. That's it. You now understand how the Android Things I2C output communication with peripherals works. You can interface with an alphanumeric character display, writing commands to control its settings, such as brightness and display characters. This knowledge also transfers to coding other I2C peripherals, such as fingerprint readers, motor drivers, or other digital displays.